Welcome to AP Biology. We're just working through the water potential practice problems, and we're on number 3 right now. So number 3 says if you are asked to estimate if a certain species of plant could live in a certain environment, and you're giving the following data. Okay, so you've got some plant here. And here it is in its environment. Okay, so overall, the water potential of the soil is negative 17 bars. And you want to know, will it live? The concentration of the plant cell, so the cells in here, concentration is 0.1 molar. And we're going to assume the ionization constant is 1, like it's mostly sugar in there. The pressure in the plant cells, so the pressure is going to be 19 bars. And it's giving us a temperature of 13 Celsius, but I know I have to add 273 to that, so I will do that right now. 273 plus 13 is going to give me a temperature of 286 Kelvin. I always need to do that conversion, and if you forget, it is also right here. It tells you that it needs to be in Kelvin. All right, so which way is it going to go? So I need to know the water potential inside the plant and the water potential in the soil. So the negative 17 bars was actually the water potential of the soil. So I already have that done. So what I need to do is calculate the water potential in the plant, and then it's going to go high to low, and we're going to hope it's going to go in, but maybe not. So let's look at the plant. Let's do the solute potential first. So that's negative I CRT, and so it's a negative 1, and the concentration it says is 0.1 molar. I'm going to call that moles per liter. I'm running off the edge here. All right, and then R is 0.0831 mole. No, what is the unit here? I'm going to look here and look at R, liter bar per mole Kelvin. I swear I have an eraser. Here it is. Okay, so liter bar per mole Kelvin. And then the temperature is, I calculated it up here, 286 Kelvin. So if I multiply all that stuff out, I am going to get, did I do that right before? I'm going to get negative 2.4. And I'm left with bars because my moles cross out, my liters cross out, and my Kelvin crosses out. So I'm just left with these bars. So negative 2.4 bars is the solute concentration. But I know that the water potential, is the solute potential. Concentration is this, solute potential. Okay, so the water potential is the pressure potential plus the solute potential. So it's set up here that the pressure potential is 19 bars. And then the solute potential is negative 2.4 bars. And so the water potential equals 19. This equals to 16.6 bars. And so that means my flower is going to die. So this is 16.6, but the soil is negative 17. We're going to go high to low. Water is going to leave. Whoops. Sorry, I should have had that. So 16.6 bars is the plant. Negative 17 bars is the soil. So water's going to go high to low, and it's going to leave. So sad. Oh my God. All right, let's do number 4. I think we can fit another one in here. Okay, number 4. A student nurse accidentally injects distilled water into a patient's veins. Oops, that's not good. Instead of isotonic saline solution, what will happen to the patient's red blood cells? All you need to say here is that the cells are going to swell and maybe lyse or break because the distilled water, it doesn't have any solids in it. So you'll have the cells like this with their, there's always stuff in cells, right? So if you put it in distilled water, it'll mix with what's in there already. So maybe it's okay if it's just a little bit, but probably not. The water is going to go from high concentration to low concentration of water, or water chases solute, right? The water is going to go into the solute, meaning from low to high solute concentration. So the cells might lyse. Okay, that's number